So in the class, we had discussed the use of multiplexer as a logic element. We had done few examples. We had implemented full adder using a multiplexer. And as of now, we have done what's known as a straightforward implementation using a multiplexer. Now here on the screen, I have a typical example wherein I have a three variable function a, b, c in that order. And the minterms that are appearing in this are 1, 3, 5, 6. So I have expanded the function here. These are the individual terms. And you know that to implement a function, logic function using a multiplexer, the nature of the multiplexer is actually determined by the number of the variables. For example, in this case, I have three variables. So we will need a multiplexer that has three selection lines. In other words, we will need an 8 cross 1 multiplexer. And the way we implement is the variables, they are actually attached, they are connected to the selection lines in the order in which they appear. For example, in this case, a, b, c will appear in the selection lines s2, s1 and s0, right? And then the main terms that exist in your function, they are actually connected to logic 1, and those who do not appear in the function, they are connected to logic 0. For example, in this case, to implement this function, what I will do is I will have a line here that will be connected to supply and then ground. So 1 is a part of this, so I will connect 1. Then similarly 3, 5 and 6. And the remaining 4, they will be simply grounded. Right? So I will have something like this. I have connected 0, then 2, then 4, then 7. And by making these changes, these connections, rather, I will have my function implemented using an 8 cross 1 multiplexer. So this kind of implementation is known as a straightforward implementation. And if you have a keen look at this implementation, you will see that the variables are actually adjusted in the selection lines. And your data inputs, they are either directly connected to 1 or directly connected to 0, depending upon whether they appear in the function or not. Now, the question here is what we are trying to look for. Is it possible to have a function implemented using a lower order multiplexer? Right? Like in this case, I have an 8 cross 1, this 3 variable function. A straightforward implementation will require an 8 cross 1 multiplexer. Now the question here is it possible to implement this function using a lower multiplexer? 8 cross 1 se niche, the next multiplexer in line is 4 cross 1 multiplexer. So I'm trying to actually, is there a method? Is it possible to have this 3 variable function being implemented using a 4 cross 1 multiplexer? And the answer is yes, we can actually do it. We can actually have what's known as a one down implementation. But you see, if I go here, I have the same function. I have function A, B, C. It has 4 minterms 1, 3, 5, 6. Fine. Now, normally what we do is these variables, they are actually connected to the selection lines. But in this case, now I only have 2 selection lines. I have S1 and S0. And these 2 selection lines can accommodate only 2 of my variables. Fine. So the procedure is that 2 of your variables, 2 of the least significant variables, B and C, they will appear as usual at the selection lines for implementing this function using a lower order multiplexer. Now what remains is the input A, is the variable A, and I have to adjust this variable A in these 4 inputs which are here. Fine. So the procedure here is we actually create a table, and maybe I should write it here. The most significant variable has to be adjusted in the data inputs. So this is the challenge, and this is something that we need to learn how to adjust this. Fine? Because as of now, in the straightforward implementation, we have been directly connecting these data inputs to either 1 or 0, depending upon whether the corresponding minterm is a part of a function or not. For this, we create a table. It's a straightforward table, and here I will create a table. It will have two columns. Fine. Because the remaining variable a, it can either appear in the complementary form or it can appear in the normal form. So it has two rows, one corresponding to the complementary form of a, another one corresponding to the normal form of a. Fine. Then I have four inputs, I0, I1, I2, and I have to actually accommodate. So I will draw four more lines to complete the table. This column for I0, I1, I2, I3. Fine. So this one is for I0, I1, I2, I3. Next, I will list all the minterms. Fine. So you know this is a three variable function. So I will have minterms 0, 1, 2, 3. Then to the second row 4, 5, 6, 7. Next, what I will do is the minterm that appears in my function, that is minterm 1, 3, 5, 6, I will encircle them. So I will encircle 1 because it appears in the function. Then 3, 5, 6. Fine. So again, repeat, I have to create a table which has two rows, one row corresponding to the complemented form of my variable and another row for the normal form of the variable. Then along the columns, I have to list the number of inputs that my multiplexer has. So here I have four inputs, so I will list them I0, I1, I2, I3. Then the cells that appear from the interconnection of these columns and rows, I have to fill up them with the minterms. Then every minterm that appears in my function, I will encircle. Fine. Then I will solve this table. And solve in the sense I have to actually come up with a value or a variable that has to be applied to these four inputs. So solve करने के लिए we go column by column. So if I start with this column which corresponds to I0, I have minterm 0, I have minterm 4, and none of these minterms are encircled. Means none of these minterms appear in my function. So I will put a 0 here. Then I go to the second column. Now minterm 1 and 5, both these minterms appear in my function. So this is encircled, this is encircled. This will result in a 1 here. Then I2, 2 is not a part of my function, 6 is a part of a function. And this 6 actually corresponds to row A. So I'll put A here. Then again for the final column, I have 3 which is encircled and this corresponds to A complement. So like this. And these are the connections you will make. So your input 0, I0 will be connected to 0, I1 will be connected to 1, I2 will be connected to A, I3 will be connected to A column. And this will actually implement your function A, B. And you can easily check, I will quickly solve this. You know that the equation for a multiplexer, for a 4-cross multiplexer is B complement C complement, first input is 0 plus B complement C 1 plus BC complement A plus BCA complement. Right? So this term will be 0, this term will be B complement C, then I will slightly rearrange this ABC complement plus A complement BC. Fine. And for this term, you can actually have two more terms to get it in the canonical form. Fine. So I will have this term, this term, this term, this term, and it is the same as this function. Fine. So we can actually, and this is the maximum we can go. We cannot implement this using a single 2x1, but we can implement it using 4x1, and this is the method we use. Now quickly, let's take an example wherein I have to implement the sum and carry of a full adder using 8x1 multiplexer. So this is my straightforward implementation. And then we'll try to implement it using a 4x1 multiplexer. This is what we call a one down implementation, because I'm using a lower order multiplexer. Now for the straightforward implementation, 8x1, 8x1, you have to come up with the equations for your full adders and for the sum and the carry. Fine. So we had done it in the class. I think for a full adder, if I remember correctly, sum is given by, so sum will be given by min terms. I think it was 1, 2, 4, and 7. And likewise, carry output carry was given by the min terms. I think it was 3, 5, 6, 7. Now, straightforward implementation is straightforward. What you have to do, your variables will be connected here in the order in which they appear. So A, B, C in, fine. Then if you have to implement sum here, whatever terms here, they will be directly connected to this supply. Fine. So the conventional method, so it will be, I will have a line here. It's slightly difficult to adjust here. Okay. Then 1, 2, 4, 7. So 1 is here, 2 is here, 4 is here, 7 is here. And the rest of the terms, they will be directly grounded. Fine. So I will have something like this. 6, 5, 3, 1, 0. So this is my sum. Similarly, if we have to implement the carry part of it, again, I will bring in a line here, a supply line, which is logic 1. So it has 3, 5, 6, 7. So I'll connect 3, I'll connect 5, then 6, then 7, and then another one, a ground line, and the rest of the terms 4, 2, 1, 0. They will be connected here, and by making these connections, you are actually implementing your output case. So this is the straightforward implementation. For one down implementation, we require 2 4x1 multiplexers. Two of your variables, they will directly apply at the selection layers in this order. Then the third variable I have to adjust. For that, I will construct two tables, one for sum. So let's first construct it for sum. So I will have a table here. Like I said, same process. I will have two rows, one corresponding to the complemented, just a second, the complemented form of A, normal form of A, fine. And I will have 4 columns in this, I0, I1, I2, and I3. Let me just erase this. Fine. So here I have, this one is for I0, I1, I2, I3. Then I will list the minterm, all the minterms 0, 1, 2, 3, 4, 5, 6, 7. Then I will encircle those minterms which are a part of the function. Now for sum, I have 1, 2, 4, 7. So I will encircle 1, 2, 4, 7. Fine. Then I will work my way column by column. Like here I0, this will give me A because this is encircled. For I1, A complement. I2, again A complement because this is encircled and this corresponds to row A complement. And I3 will be connected to A. So if I make these connections, I connect I0 to A, then I1 to A complement, I2 again A complement, I3 to A. This will implement my sum. Fine. Similarly, for output carry, I will create a similar table. Let me just quickly create it, which will again have two rows, one corresponding to the normal form of A, and not normal, corresponding to the complemented form of A, and other one normal. And then, like in the previous case, I0, I1, I2, and I3. These are the inputs for which I need to find the value. List all the minterms 0, 1, 2, 3, 4, 5, 6, 7. Then encircle those minterms which are a part of your function. So that means 3, 5, 6, and 7. So 3, 5, 6, 7. Then we'll work our way column by column. This column has none of the encircled cells, so 0. This corresponds to A. This one again A. This one has both the cells and circles, so on. So if I make these connections here, so this will be 0, A, another A, then 1. This will implement my output carry. Right? So this is how I implement a full adder using 8+1 straightforward implementation, and then 1 down implementation, which means using 4+1. In the next videos, we'll take some more examples. Let's stop here.